Thermodynamics. Thermodynamics refers to processes that involve heat transfer. U is the total internal energy of a system. Say that to your English teacher, drive them nuts. U is the total internal energy of a system. Now that total energy comes from the kinetic energy of each of the molecules in the system, which depends on the temperature. This is the equation for the average kinetic energy of a single molecule. It's 3/2 times Boltzmann's constant times the temperature measured in kelvins. These are constants, so you can see that the energy depends directly upon the temperature. So the internal energy is, we're going to take this energy of an individual molecule and multiply it by how many molecules there are. So we get 3/2 times the number of molecules times Boltzmann's constant times the temperature. Now in physics, we try to use the number of molecules in Boltzmann's constant. In chemistry class, they use the number of moles and the gas constant. So this gas constant is basically Boltzmann's constants, and then they're multiplying or dividing by Avogadro's number. This is an easier constant to remember, but you have to know how many moles there are versus how many molecules there are. Q is the heat energy added to a system. And work is defined as the work done by the system. The important part of these definitions is where it's applied to. Q is added to the system, work is done by the system. Our work formula is pressure times the change in volume. So as our volume gets bigger, we're doing work to do that. Thermal equilibrium is a uniform temperature that is reached after two bodies have been in contact for a period of time. An easy example of that is we take a Coke bottle out of the refrigerator, we put it on the counter. That Coke is going to warm up. It's in contact with the environment, and because there's a temperature difference, energy or heat is going to flow. In this case, it's flowing from the air into the bottle to warm the bottle up. So my Q is going to be positive because we're adding heat to the system. Likewise, if we take a cup of coffee and put it out, the coffee is hotter than the air, so this one is going to be giving heat to the atmosphere, or we'll say that heat is removed from the system, and that's why my Q would be negative for the coffee. Now to reach thermal equilibrium, it takes some time for each one of these to become the same temperature as the air. Once the air and the coffee are at the same temperature, we say they are in thermal equilibrium. In general, everything in the room is at room temperature. It is in thermal equilibrium already. It's only for a hot item or a cold item that we have to have a heat exchange go on before it becomes in thermal equilibrium as well. The thermodynamic processes need to be memorized. First one is isothermal process. This takes place at a constant temperature. What we have to memorize about this is that there's no change in internal energy. I'll explain that one a little bit. P times V equals a constant. And then we should be able to cite some examples of these. The example I put in the notes is gradually inflating or deflating a balloon, and we do it slowly. That's the key part in isothermal. It takes place slow enough so heat from the environment can transfer in or out. A better example of this is if we take a bag of potato chips in the car and we drive up in the mountains. As your altitude gets higher and higher, the pressure is going to change, which makes the volume change. That potato chip bag gets very big and puffy, and during the drive the change is happening slow enough that the temperature stays pretty constant because you're in the same environment during the entire drive.
Focus. Oh, there it goes. Okay, that works.
We got it. Oh no, this is proof. So if Luke's two bags that we bought him first, you know, we had to eat them.
What are we at as far as altitude?
We're at 7,846 feet.
And the Lay's potato chip bag did not make it.
Yeah.
Okay, so the graphs of all of these processes need to be memorized as well. This is the isothermal graph. If I go back up here and look at P times V equals constant, I can divide both sides by V, and what we get is the equation for an inverse graph. The PV diagram for an isothermal process is an inverse graph, P equals constant over V. I want you to have this picture in your notes, and then I also want you to add to it if we have two inverse graphs. They both have the same equation, but they'll have a different K. One will have a higher temperature and one will have a lower temperature. This also needs to be memorized because we need to recognize when you're on a PV graph, when you're moving to the right, you are increasing temperature, and when you're moving upwards, you are increasing temperature on the PV graph. Adiabatic process is a process that has no heat transferred in or out during the process. The pressure, the volume, and the temperature all change in this one. Work is done, your volume's changing, so P times delta V is your work. The example that they give this is rapidly inflating or deflating a balloon. The key here is rapidly. You need to do it quick enough that heat cannot transfer from the atmosphere. If you ever squirted a can of compressed air, you find out that that can gets cooled very quickly. This is an adiabatic process. All three things are changing as the gas is coming out, the pressure is changing, the volume of it's changing, and that temperature cools down quickly. And it happens so rapidly that there's no time for the heat of the atmosphere to warm the bottle up. Here's some more examples.
Okay, Aaron.
All right, so Aaron,
This is a little bit of a science experiment. I don't know what is at play here, but Aaron
it's like an air can that
Aaron is turning the air can upside down and sending some. Oh! Oh! Look at it go!
That is incredible. Did you freeze it?
That is incredible. Look at it; it's all disappearing too. Oh, it's so cold.
Here, keep your hand there. I'm gonna...
Yeah, do it on your.
Oh no!
Oh,
no! Please no!
Are you ready?
It's gonna...
Aaron.
Oh, burns on my hand. It just went away pretty quickly, but
Oh my God.
Ooh, that smells weird.
Steal my paint off or something. Oh my gosh, it worked.
okay, the graph of this one is very similar to the isothermal graph, so I put them both on the same so you can see them. Sometimes it's hard to tell just from the shape, is this the inverse graph or is this the inverse graph? And that's why we have to use the test, P times V equals a constant. Usually on the graph they'll give you two numbers of pressure and volume for the starting and ending points, and you can multiply those and see if that PV is a constant, that's the isothermal. If it's not a constant, it's an adiabatic graph. Isovolumetric or isochoric means constant volume. That graph's easy, just a vertical line. Could be going up or going down, depending on how our pressure is changing. If the volume is not changing, then no work is done, because work is pressure times a change in volume, and that change is going to be zero in this process. Example would be heating a car in the sun. The volume has to stay constant, or we have a container such as a can or a bottle. Isobaric process means we have a constant pressure. So looking at the graph, we have a flat line like this, and this time our volume is changing, so we do have work being done, P times delta V. Example of this would be gas in a piston is slowly heated and expands, and it pushes the piston upward. Again, the example is occurring slowly, so there is time for heat from the atmosphere to transfer in and out. When we're calculating the work, we have an initial volume and a final volume and a constant pressure. So when you're multiplying those, you're finding the area underneath this graph. So the work is actually the area underneath a PV diagram. First law of thermodynamics, I'm going to start with an example. I have a cylinder with gas in it, and this is a piston compressing the gas. Now if I add some heat to this, that heat is going to make the molecules move faster, Those faster moving molecules are going to hit the piston and push it upwards and do some work. The first law of thermodynamics is just the conservation of energy. We're taking this much energy, some of that energy goes into moving the piston, and some of that energy goes into making the molecules move faster. So this is how I write it. The change in internal energy, how much faster we got those molecules to go, is my total energy minus the work that was done. Reading the equation, we have the change in internal energy equals the heat added to the system minus the work done by the system. Notice that I'm including the definitions of Q and W in this equation. The important part of that is where it's applied. The heat is added to the system, the work is done by the system. Let's look at our work formula. Work is pressure times change in volume. Notice that volume increased, so we had an increase in volume. That means work was done by the system. Now our textbook looks at it a little bit differently. They take our gas inside the cylinder and they ask what are two ways that we can increase that energy inside the cylinder. We can do it by doing work by pushing the piston down. If I compress it, that's going to make these molecules move faster. And we can also make them move faster by adding heat. So their equation for the first law of thermodynamics is that energy of those molecules depends on two things, the heat I added and the work I did to it. So reading the equation says the change in internal energy equals the heat added to the system plus the work done on the system. And that right there is our key. Is it positive or is it negative? Now if we look at the work formula, work equals pressure times the change in volume. When I squeezed this, the volume got smaller, so we had a negative change in volume, and that means the work was negative. So when I'm doing work on the system, the work is negative. So what I do is just take that minus sign and put it in the equation, and that way it all makes sense. All right, the second law of thermodynamics can be stated in many ways. I'm going to say it this way. Heat flows from hot to cold. It can never flow from cold to hot. We talk about the second law of thermodynamics when we're looking at heat engines. Basically, a heat engine, we have two different temperatures. We call them reservoirs. This is a high temperature reservoir and a low temperature reservoir. An example would be like burning gasoline makes a high temperature, and the air outside your engine or outside your car is the cool temperature. And heat always flows from a high temperature to a low temperature, is the second law of thermodynamics. So the idea of a heat engine is we're going to take that heat and put it into a system and have that system do some work for us. And then whatever energy is left over will come back out to the lower temperature. So looking at the conservation of energy law, Q in was the energy that I put in, and we got two things out. We got work out and we got heat back out again. So that work can be calculated if I take the total energy and subtract what came out of it. I can figure out how much work was done. Whenever we talk about engines, we're asked about efficiency. Efficiency is the work output divided by the work input, and we express this as a percentage. In this case, the input was the heat that we put in, and the output was this work that our system is doing for us. So we would write it this way, work out divided by Q in. So the work output would be something like gas inside the cylinder expanding and pushing the piston up for us to do our work for us. Here's another way to calculate the efficiency. It's the difference in the two temperatures, and in all of these thermodynamic formulas, temperature has to be done in kelvins. So it's the difference in the temperature divided by the high temperature happens to come out to the same number as the work out divided by the work in. All right, let's look at an example problem from our old textbook. We have a thermodynamic process graphed here. This is a PV diagram. To solve a problem using the PV diagram, these are the equations we need to have memorized. Work is pressure times change in volume. The first law of thermodynamics, the change in internal energy is the heat added minus the work done. The ideal gas law, PV equals nRT. And the internal energy is proportional to the temperature. This was the equation U equals 3/2 times NKT, or 3/2 times nRT. You don't have to remember the whole equation, you just need to know that the internal energy depends on one thing only, and that's the temperature. So the first thing is asking us to find the total work done from A to B to C. And work is pressure times change in volume. So I look for my graph from A to B to C. I know from A to B there's no work, that is a isovolumetric process. From B to C is an isobaric process. So the work is going to be the area underneath that graph. So for area, I'm going to do the change in volume down here, 9.3 minus 6.8, and multiply by the pressure, 1.6. Now in chemistry, they measure pressure in atmospheres. In physics, we use pascals. And in chemistry, they use liters or cubic centimeters. For volume, we use cubic meters in physics. So we have some conversions we need to know. This first one is on your AP sheet. 1 atmosphere is 1 times 10 to the 5th pascals. We use pascals in physics because that's the one that has newtons and meters, so we can use it with our other units. And 1,000 liters is 1 cubic meter is our other conversion. Right, so my formula, I have pressure times change in volume, but I have to do a conversion for each of those to get all the units come out right. And this one comes out to 350 joules. Next it asks me, find the change in internal energy if I go from A to B to C. For the change in internal energy, you're looking at your starting point and your ending point. The pathway doesn't really matter. We're just looking at the temperature. As I mentioned before, if you go downwards, your temperature is decreasing. If you're going to the right, your temperature is increasing. If this is an isothermal line, that means we started and ended at the same temperature, and that means my change in internal energy is going to be the change in temperature, which is 0. So what we have to do is figure out, is this an isothermal graph or is it an adiabatic graph? So our test for that is pressure times volume is a constant. So I'm going to take the pressure times volume at point A, 2.2 times 6.8 comes out to 15. And I'll do the pressure times volume at point C, 1.6 times 9.3, also comes out to 15. Because these match each other, we have a PV is constant, and that means this is a isothermal process. So the change in temperature was 0, and that makes the change in internal energy 0. The last part is asking to find Q from A to B to C. So this is our pathway. And the only one of these equations that has Q in it is the first law of thermodynamics. So if I add a W on both sides, Q is going to be the change in internal energy plus the work. The internal energy change was 0, so I'm just going to cross that out, and that means the heat added to the system equals the work done by the system, which is 350 joules.
So, Nigel, what have we got here?
Oh, we've got something called a fire syringe.
And what does it do?
Oh, well, I'll show you what it does. Some cotton wool in there.
Okay.
I'm just going to compress the air in it, and hopefully it will. I don't know what it's going to do.
Wow.
That's pretty cool.
You made a spark in there. Was there any source of fire, like a match or anything down there?
Well, as you can see, it's pretty transparent. There was no match in there. It was actually just the compression of the air on top of it, which was able to ignite the cotton wool that we had in there.
So you're saying if we compress air, we can make it hot enough to ignite cotton?
Yeah, because air is made up of particles, so when you're actually compressing it, you're forcing those particles to collide closer together, which is actually going to raise the temperature in the inside of that tube there.
Okay, can you describe the apparatus for me?
Well, all there is there's a glass chamber in there where the cotton wool sits, and as you can see, there's this piston that moves up and down into that glass chamber, and as it moves up and down, you can actually compress the air.
So it's like a little plunger?
Like a little plunger, yeah.
Okay, so why don't we set one up so we can do it again?
Do it again? Okay, I'll clean the remnants out.
What are the tricks here?
The trick is to get not too much, but not too little cotton wool, and it's good to get it aerated so that there's a lot of air around it, so it makes it much easier to ignite, just like a good fire.
Is it just me, or do you feel like we're on a cooking show?
I feel like we're on a cooking show, yes.
Who do you think would be Jamie Oliver in this situation? Would it be you or me?
I'm more manly, so
He's more like Nigella Lawson, let's face it.
that's a good play on words. I wish.
All right, we're ready for this?
Yes. Simple as that. Obviously, no matches, no switches, no anything.
Okay.
We'll try it. Again?
You want me to try?
You can try it.
Yeah, do you wanna hold
do
it?
you have the strength?
We're going to find out,
We'll
aren't we?
find out. This is going to be awkward for Derek, I think.
Okay, so what I'm going to try to do is compress the air in there, and by compressing it, I'm going to increase its temperature because we're pushing all these air molecules together. And if I get it hot enough to the ignition point of cotton, hopefully the cotton will catch on fire.
Yeah, I've heard that the auto ignition temperature of cotton is about 400 degrees Celsius, so you can get quite enormous amounts of temperature from a very quick compression.
3, 2, 1.
Oh, surprise!
Beginner's
It
luck.
worked, yeah.
Yeah, check that out. So I guess we could generalize and say if you do the compression quite slowly, then, well, there's time for the heat to escape out of the air. And so we don't actually get a high enough temperature to cause the cotton to ignite.
Yeah, and there's actually a word for that. It's called an adiabatic compression. That's the one where there's enough heat generated quickly enough so that we can get that auto ignition.
Yeah, so an adiabatic compression would be one in which the heat doesn't escape from the gas.
Doesn't have the time to.
Absolutely.
Yeah.
All right. Well, let's go see if we can auto-ignite some other things.
Yeah, maybe some hair.
Okay.
Maybe not a good fuel source.
End of notes.